Okay, now we'll begin with James Chadwick. The final piece of the puzzle was that unaccounted for mass. So we had the protons and we had the electrons. And we knew that there was a mass difference, but we couldn't figure it out. So James Chadwick comes along and he solves the neutron problem. He figures out that there must be a particle devoid of electrical charge. And he said this new tool in atomic disintegration need not overcome an electric barrier and is capable of penetrating and splitting the nuclei of even the heaviest elements. His thoughts on this become the door that opens up the possibility of building an atomic bomb. So the reimagined atomic nucleus, you had those energy levels again, and in the nucleus we now found neutrons and protons and electrons. And that, ladies and gentlemen, is Pandora's box. Without the neutron, we did not have the understanding on how to build a bomb. You had to have a particle that you could throw at the nucleus to cause a reaction. Chadwick he does work on the atomic project throughout World War II. A little side note, he actually spends the rest of his life taking sleeping pills just to get some sleep. He suffers from severe insomnia. He recognizes what he has done. Lisa Meitner, she is known as the German Madame Curie by Einstein. She's an Austrian physicist. She co-discovered the origin of nuclear fission in uranium with her nephew Otto Frisch. She does flee Germany after Hitler becomes chancellor. Bohr aids her in getting her out of the country. We also credit her with figuring out about isotopes. She had figured out, based on information that Otto Hahn had been sending her, she figured out there must have been a possibility of element 93. She needed a cyclotron to determine if the element that had decayed was indeed element 93. However, war would actually prevent her from solving this mystery, and she considered it one of her largest mysteries that she had wished she had solved. So, what is this radiation we're speaking about? So, radiation, there are three branches at this point. It's called alpha, beta, and gamma. And alpha is your largest particle, and it's the easiest one that we can stop. It can be blocked with paper, okay? Its charge is positive, and it can be deflected by a magnetic field, okay? Beta particles are high-energy electrons, and they have more penetrating power than alpha particles, but they can be stopped with aluminum, 3 millimeters of aluminum. And they can be deflected by a magnetic field more so than an alpha, and in the opposite direction because they have an opposite charge. Gamma rays are the most penetrating of all. Some will argue that the penetration depth is forever. We can block it with several meters of concrete and lead. They are not deflected by a magnetic field. Otto Frisch is also an Austrian physicist. He is a co-discoverer of the origin of nuclear fission in uranium with his aunt, Lisa Meitner. He independently discovered spontaneous fission. And we're talking about a chain reaction. We're talking about spontaneous fission. He coined the term fission based off of biology and about, you summarize the biological processes of nuclear fission. He coined it from that, and Bohr actually thought it was kind of childish, but it caught on. He co-authored the Fritz Perls Memorial on critical mass, and he worked on the Manhattan Project, which was the American version of the atomic bomb development. His father, a few notes about him. His father was in prison in Dachau concentration camp. He was eventually granted a Swedish visa in 1939, but his father was in the concentration camp for a while. He examined the fast and slow neutron bombardment of U-235. He refined the mathematical formula for calculating the critical mass of material required to support a nuclear chain reaction. And that was originally developed by Francis Perrin. Nobody knew the rate at which U-235 would be fissioned by fast neutrons because nobody had ever separated enough of the isotope to measure. And that was the key thing, because you have U-235 and you have U-238, and majority of uranium is going to be 238. What you need for the bomb is uranium-235, but you have to be able to control the fission rate of it as well, and that's what we get into fast and slow neutrons. And the key thing about the calculation he does is that after he does the calculation, he realizes you only need a few pounds to make this bomb possible. And this is the moment he's like, oh my gosh, like this can really happen. The amount that he figured out is basically about the size of a golf ball. So, and this is what we're talking about. So we take our target nucleus and we project a neutron at it. And since you throw that neutron at it, you get an instability of that large nucleus because it's trying to hang on to all its protons and neutrons. And when you hit it, all of a sudden it can't hang on to all that. And so it splits into another element, and this will continue until you get down to a stable atom that it can finally be happy with. Okay, this is what we're talking about, a chain reaction, and it just keeps going and going and going until you finally get one that's stable. Otto Hahn is a German chemist who worked with Lisa Meitner, and he discovered with Fritz Strassmann evidence for nuclear fission in uranium. He would send his work to Lisa Meitner as he's trying to figure out what's going on. He is captured and detained at the hall where he won a Nobel Prize in chemistry. A few other things about him. Strassmann, they couldn't explain how the current atomic model coincided with what you're finding, and that's a huge driving point for the development of the quantum model, because what we had at the time didn't work to explain it, and which is why a lot of this work really does determine the new model. He discovered that U-239 formed when 238 was captured by a neutron. It's unstable and undergoes radioactive decay within 23 minutes. He believed that there was an emission of a beta particle from U-239, which turns to a neutron into a positive proton, would therefore transmutate the uranium nucleus and make the new element 93, which is what Meitner was also working on. It does not occur in nature, so it's our very, very first element that we made ourselves. Okay, huge thing there. Because all of a sudden now we can make elements. Whoa, wait a minute, this, what? We couldn't at the time. But now we figured out that we can if we hit it just right with the neutrons. And if you could do that, then you could easily make the material that you need to make a fission bomb. So instead of having trying to go find U-235 and separate enough out of 238 to get your U-235 that you need for the bomb, instead just make it yourself. Americans Edward McCallum and Philip Abelson will also confirm this. They published it in Open Literature in 1940, and he does use the cyclotron and Joliet Curie to begin work on developing the atomic bomb. He does try to use graphite instead of heavy water. He finds out that graphite is problematic because it has to be pure graphite in order to be a good moderator for the neutrons for development of the bomb. Ernest Lawrence is from the University of California. He's the one who invents the cyclotron, which is basically a particle accelerator. He made the very first one for like $25. And it artificially induces a nuclear reaction. And it does it with a manipulation of magnets and electricity. This is the beginning phases of the Large Hadron Collider. And then we have Albert Einstein, who came up with the theory of relativity, E equals mc squared. Mass could be converted into energy, which was a huge thing, because when we were talking about law of conservation, and we said that you had law of conservation of matter, law of conservation energy, it is during this time that we figure out those two actually belong together. Because when they were doing these reactions, they were finding out that the matter that they started with was not what they were ending with at the end. there was about a 1/5 that they were losing. And so they finally figured out that it was being converted to energy. So the neutron causes the uranium nucleus to split, which then causes a conversion of mass into energy. Okay. He also writes a letter to Roosevelt in regards to the atomic bomb being possible. He was asked by Leo Szilard to actually write to the Queen of the Belgians, but he wrote it to Roosevelt instead. He was given credit. He won a Nobel Prize for the photoelectric effect, which basically points out that if you have the right frequency of light and you shine that on a surface, a metal surface, you can actually eject electrons, and therefore you can cause electricity. The photoelectric effect is one of our main points when we start developing the quantum theory. In classical, we would have said that the intensity of the light determines when electrons are ejected, but with quantum mechanics, we say it's actually the frequency of the light. We would say that the kinetic energy of ejected electrons depends on the intensity of light. With classical, it's actually the frequency of the light. And with classical, we say that it takes time for low intensities to eject the electron. And quantum mechanics says, nope, it's pretty much instantaneously as long as you're at the right frequency. So we have a lot of development on the development of the atomic bomb, which actually develops our quantum model, including Einstein's theory of relativity, which actually explained what was happening with the bomb and that we could actually make it. So lots of Pandora boxes opened up all of a sudden.